Thank you very much. And, well, thanks to the organizers for inviting me here. I really enjoy it. It's a very nice place. I will talk about rearrangements. And, well, let's just start. First, I have to say a little bit about the authors. I mean, this is joint work. And actually, I got into this work pretty late. So first, other people started with this, and then at some point, they asked me some questions. Actually, Paul Larsen asked me some questions, and then we worked together on that, and so I got into this work. So it's joint work with a total of, I think, 6 people are listed here. But, well, as a matter of fact, there are 2 papers. And I will talk mainly about, or almost exclusively about the first one. The first one exists as a preprint. It has been submitted. The second one is still in preparation. And, well, I don't know how much time I will have, but I will talk a little bit about the second one right at the end of my talk, if time permits. So, yeah, about the people here, I think the first paper is with the first 5 people, and then the second paper is with Will, Joel, and with Jonathan. At least that's the plan right now. As I said, this is still work in progress. Okay, so that's on the set theory side. Now, a couple of days ago, I actually realized that what we did for rearrangements, something similar also has been done much more recently by people in computability theory. And since I think there are more people in computability than in set theory in the audience, I will also mention their results, even though I'm not directly involved in this. So this is work of Ungai, Valverde, and Tveit. I think they're from Wisconsin. So that's on the computability theory side. And yeah, once in a while I will mention some of their theorems and how they relate to our work. There is a preprint. I mean, they have a preprint, but this preprint is very recent. It appeared in the archive like, I would say, 2 months ago, something like that. Okay, so that's sort of the introduction. Of course, you should feel free to ask questions at any time and also tell me if I'm too slow or too fast. So the first slide is really boring, I guess. So that's just about series, about very basic things about series, which you learn in the very first semester as an undergraduate at university. So suppose we have a series. A series is called absolutely convergent if the series of its absolute values converges. If that's not the case, but the series still converges, then it's called conditionally convergent. And my talk will be about conditionally convergent series, and since I don't want to write out the word all the time, I will just say CC for conditionally convergent. Okay, so what does it mean? It means that the series itself converges, but the series of absolute values does not converge. So, of course, it means that the sum of absolute values is plus infinity. Let me make some very basic notes about convergent series. If you have a convergent series, then, of course, the sequence of terms must go to 0. I mean, that's a very basic fact. That's also something you learn in the first semester in undergraduate studies. One more comment is about conditionally convergent series is the following. If you have a conditionally convergent series, and you only look at the positive terms, so this one is the sum over the positive terms. So P is a set of positive terms, and it's a set of negative terms. Then the set of positive terms must sum to plus infinity, and the set of negative terms must sum to minus infinity. That's a basic fact about conditionally convergent series. I mean, you can just check this. I mean, because if this sum is finite, then to make the whole thing converge at all, then this one also must be finite, and that's the case when we are absolutely convergent. And if here one of them is infinite and the other one is not, then the series cannot be conditionally convergent. It cannot converge at all. I mean, that's also trivial. Okay, now again, a basic fact about conditionally convergent series. That's again something you learn in calculus or analysis 1 in the first semester of undergraduate studies. Is Riemann's rearrangement theorem. If you have a conditionally convergent series, then you can rearrange its terms and make the rearranged series to converge to any number you like. So you can take any real number, and then you find a rearrangement. A rearrangement means that you sort of rearrange the terms of the series. So rearrangement is basically given by a permutation of the natural numbers. I use sim omega for the group of permutations of natural numbers here. So there is this rearrangement. So the rearrangements, obviously, as I said, get identified with permutations of omega, such that this rearranged series converges to R. And not only you can make it converge to any other finite number, you can also make it diverge to plus infinity. You can make it diverge to minus infinity just by an appropriate rearrangement. And that's actually just using this fact which I mentioned before, that the positive terms converge to plus infinity and the negative ones to minus infinity. This kind of thing is not hard to show. Also, of course, there are many permutations or many rearrangements such that neither of the above happens, namely, it does not converge to a finite number, it does not diverge to plus or minus infinity. This case we call the case of divergence by oscillation. So it sort of oscillates, and so if you look at the set of accumulation points, this set has to have at least two elements, two or more elements. Of course, they could include plus and minus infinity. Another way to say what divergence by oscillation means is if you look at the partial sums, at the finite partial sum, so this is a finite partial sum here, then the lim of the finite partial sums is to be strictly less than the lim sub of the finite partial sums. Of course, either of these values, I mean, this lim can possibly be minus infinity, the lim sub can possibly be plus infinity. That case is also included here. Okay. Okay, so far so good. And now, okay, I'm a set theorist, so a very natural question to ask is, we know that for every series we can find such a permutation, but you can ask how many permutations do you really need for this? So how many permutations do we need such that for every conditionally convergent series there is a permutation in our family, there is a rearrangement in our family such that the rearranged series no longer converges to the original value, which means it may converge to another finite value, to plus or minus infinity, or it may completely diverge. So that's the question we asked, and of course this naturally gives rise to a cardinal. Now, as I mentioned before, people have looked at this also in computability theory. So the computability theoretic question, it looks a little bit different, but I will say a little bit more about it. It's about a Highness property in the Turing degrees, and it looks like that. So what is this Highness property? I mean, how strong it is really the question. So what does it mean for a real? I mean, how strong a property is that to compute a conditionally convergent series of rationals? Here we only look at series of rationals because everything wants to be computable, such that for every computable permutation, the rearranged series still converges to the same value. Of course, this must be a Highness property. So clearly, such a real cannot be computable itself because it has to compute this, let me rather say such a series of rationals cannot be computable itself, because for computable one, just using a computable version of Riemann's theorem, you actually find a computable permutation which makes it converge to something else or diverge or whatever, you know. So this is a Highness property. Okay, let's first look at the cardinal. Now, actually, because we have these various cases like convergence to a different finite sum and also divergence to plus and minus infinity, divergence by oscillation, we actually get several cardinals. So the main one is the rearrangement number. So this is the one I will mainly talk about. And that's just the minimal cardinality of a family of permutations, so of a subset of sim omega of the permutations of the rearrangements, such that for every conditionally convergent series, there exists a permutation in this family such that the rearranged series does not converge to the original value. This is sort of a shorthand, so I just said it in words what I intend here. This is just intended to mean that the rearranged one does not converge to the original value. So here actually three things can happen. Either it converges to another finite value, or it diverges to plus minus infinity, or it diverges by oscillation. All three are allowed. In this definition, I don't care. Okay, then we get some other definitions. For example, we get this RO. The O stands, of course, for oscillation. So that's the minimal size of a family of permutations, such that for every conditionally convergent series, there is one in this family, such that the rearranged series diverges by oscillation. So here I'm more specific. I want divergence by oscillation. And then, of course, we can just continue with that. And we get Ri. So this is, I stands for infinite, I guess. Even not sure, but I mean, I was not the one who defined that. It's a minimal size of a family of permutations, such that for every conditionally convergent series, there is somebody in this family, such that the rearranged series diverges to either plus infinity or to minus infinity. And then the last one, this has an F, and F stands for finite, because now we look at finite values. So it's the least size of a family of permutations, such that for every conditionally convergent series, AN, there exists a permutation in this family such that the rearranged series does converge. So with convergence, I mean convergence to a finite value. It does converge to a finite value, but this finite value is different from the original one. Yes?
If you make another one, say you just want that the pi of AN converges to 0, gives this another cardinal?
I think then you need probably, I think that will give you continuum, because, let's see. I have to think about it. I will answer it later. After, we can talk about it afterwards. But I think it gives continuum, because, right, why is that? Or maybe not. Okay, well, I'll think about it. Let's see. So now we have 4 cardinals just to see what's going on here. Of course, in the second, third, and fourth definition, we are more specific. So every pi, I mean, every family of permutations which works for either the second, third, or fourth definition also works for the first one. So we obviously have these relations. This is, of course, this is not the optimal diagram. I will say more about this in a minute. But, okay, so there are many definitions here, but I will come back to the definitions. They will also be on other slides. So let's continue. Here are the Highness properties. There are only 2 of them. I will say in a minute why. The first one corresponds to this one at the bottom. It says the following. So here we assume we have a conditionally convergent series of rationals, and we say that this series is computably imperturbable if for all computable permutations, the sum is still the same. So we still converge to the same value. So this is the one which corresponds to this. Well, let me just say imperturbable. And then the other one, so this is of course from this paper of Ongay, Valverde, and Tveit. We say that a series of rationals is weakly computably imperturbable if all computable permutations, the sum of AN is either the same, so either they are the same, it still converges to the same value, or it diverges by oscillation. And this corresponds, well, the weak one corresponds to these 2. Now we will see why. I mean, they could have defined more. They could have defined a cardinal, a notion corresponding to each of the 4 cardinals we had before. We only had 2 of them.
Could you say one word why this is possible? I mean, if you look at Riemann's proof, where Riemann just said that you sum up the elements until you get above the threshold. So you give me a number R, and then I'm just summing up, so A0, A1, A2 until I'm above R.
Right.
So, and then I'm just taking, so obviously the positive ones, if R is positive. And now, if I'm above R, then I'm just subtracting, so adding the negative ones.
Sure.
Until I get the first one below. And then I repeat the process. Now
Sure.
I'm adding again that I get above.
Sure, yeah.
And that is converging. So that is computable in my view, the permutation. If you give me R, I can compute the permutation.
The sequence of the AN is not recursive.
Not recursive, otherwise
No, the AN is, if the, you see, if the AN here cannot be recursive, because if the AN is recursive, then maybe this is what you said, then you can build a computable permutation which makes it diverge by oscillation, for example. I mean, the original sequence is not computable. I mean, if AN was computable, then we can find a computable permutation such that this is fails.
Just a mapping from N to the rational.
Not a computable one, a not computable mapping. It may not be computable. Yeah, exactly. Imagine a mapping where the mapping from N to AN is not computable.
Yes, so for what they are, for which
Yeah.
Now I have.
Yeah.
That is
Okay, maybe it's a little bit difficult to see now the connection to the cardinals, but I think this will become clearer. In particular, I mean, why, for example, you could ask, why didn't they define a notion which corresponds to this one? And this will be on the next slide. So let's see. I mean, well, in general, it could be said, I mean, if you look at this notion here, for all computable permutations, I want that it converges to the same value. If you look at the cardinal before, so you have to look at the top cardinal. Here we say, basically, it's a negation of the statement here. So all of the statements which are in the Highness degrees are sort of negations of the statements in the cardinals. So basically, what would it mean for pi not to fulfill this property? It would mean there is such a conditionally convergent series such that for every permutation, this value is still the same. And that exactly corresponds to this definition. This is the connection between the two. This is how you should look at that. And for a similar reason, actually, this one corresponds not to either of these 2 cardinals, but to a third one, which is sort of below these 2, which is defined by saying, OK, we allow both possibilities, basically. That's how it goes. Sorry, no, I mean, of course, this notion here. OK, anyway, let's first see why didn't they define a notion for that one. The point here is, and that's on the next slide, here I have again the definitions of the cardinals. These 2 cardinals are simply the same. I mean, as I observed already, it's obvious that this one is below that one. So why is the converse true? This is actually relatively simple. So we have to prove that RO is less or equal than R. And as I said, so R is the minimal size of a set of permutations such that for every conditionally convergent series, there is one in the set such that it does not converge to the same value. And for the second one, we rather require that by the permutation, it diverges by oscillation. We use the following basic fact. I'm not going to, I mean, everybody can sort of make a proof of this. And again, this proof, of course, then if you look at the computability theory side, you would have to give a constructive proof of that, but that's also not a problem. If you have a permutation, then you can find another permutation such that infinitely often the new permutation, sigma pi, maps the first n many numbers exactly to the first n many numbers. So it's sort of a bijection on n. And also for infinitely many n, sigma pi maps the first n many numbers exactly where pi maps the first n many numbers. And it's clear you can construct this. I mean, you do this recursively. You make this task true. I mean, how can you make it true? You have an initial segment of your sigma pi, and then you have to, in infinitely many steps, you can just map things so that this is the same. And then in the next step, you make this one true. Infinitely many steps, you can make this statement true for some number n. And so you do it sort of like that. OK, now why is this helpful? Suppose you have a witness for R. With a witness, I mean a pi, a set of permutations, which satisfies this statement here. Then if you take pi together with a family of all sigma pi, this will be a witness for RO. Why is this true? Well, you simply take any conditionally convergent series AN, and so you take some AN. And now you know that there is somebody in your family pi such that the A pi n does not converge to the same value. Now, of course, there are various options. Either this already diverges by oscillation, then we are done. Or this diverges to plus or minus infinity or converges to another finite value. In this case, the argument is the same. So let's assume this is another finite number. So these are both different finite numbers. Now, if we now use sigma pi, what does sigma pi do? Well, infinitely often, sigma pi is equal to the identity, and infinitely often it's equal to pi, sort of, I mean, on some initial segment. But this means that if you look at the finite partial sums, infinitely often the finite partial sums are close and closer to this value, and infinitely often they are closer and closer to this value. So actually both of these values are accumulation points they are both accumulation points of the new one, A sigma pi n. And therefore, in this case, we must get divergence by oscillation. And that's the whole argument. So this is actually quite a simple proof, but this means that we have one cardinal less. I mean, we don't really need to consider this. OK, let's continue. The next proof is also relatively simple. Non-meager is the least size of a non-meager set of reals by definition. And it doesn't matter whether you look at the classical real numbers or you look at the Cantor space or the Baire space or whatever. OK, it's a definition. And then this rearrangement number, the original one, the one at the bottom, which is actually equal to RO, it doesn't matter. This is bounded above by non-meager. So this cardinal is less or equal than non-meager. If you look at this from the point of view of Highness properties, this means that, well, this statement is a little bit difficult maybe. If X is computably imperturbable, so it has this property, then it implies the property which corresponds to non-meager. So there's also a Highness property corresponding to non-meager. This is called weakly meager engulfing. This was defined some time ago. But it's actually equivalent to some better known notions from recursion theory, namely the disjunction of high or DNC. So high or DNC is equivalent to that one. Anyway, this, of course, this theorem is proved in this other paper by Ungay, Valverde, and Tveit. And I'm not going to go into details of this, but I will show you the basic argument of the proof. Of course, the basic thing, I mean, the proof is exactly the same of the two theorems, basically. Of course, if you look at it from the point of view of computability theory, sometimes you have to think a little bit about whether, I mean, to make everything, you know, constructive, sort of. OK, so let's assume we are given a conditionally convergent series, and we are also given some natural number. We think of it as some big natural numbers. Now, we look at the set of all permutations in sim omega such that for some n0, the finite partial sum up to n0, so a pi n, is bigger than k, and this is an open dense set. Now, of course, I'm looking here at sim omega. Now, sim omega has a natural topology, and basically it's just the subspace topology it gets from the bare space. So you look at all functions from omega to omega. You give omega the discrete topology, and you give omega to the omega the product topology, and sim omega is a subspace of this. It's actually homomorphic to omega to the omega. So basically this is the same as the bare space, and we look at the standard topology of the bare space. So of course, when we now talk about open dense sets or G deltas or meager sets or whatever, we talk about open dense or G deltas or meager sets in sim omega. We look at this as a topological space. And then I'm saying that this set here is open dense. And that's actually very simple, because if you have, I mean, my conditionally convergent series here is fixed. I just look at one for the time being. But if we have an initial segment of a permutation, then of course I can make this initial segment of the permutation longer so that this statement here is satisfied. And how do I do this? Well, I just put lots of positive terms. And as I observed right at the beginning, the sum of all the positive terms must be infinite. So by putting enough positive terms next, I can make it arbitrarily large. And putting positive terms means just defining the extension of this finite permutation in such a way that next we get many positive terms. And so this means that any basic open set can be extended to a bigger basic open set which has this property, and this just means, this is just what it means to be open dense. Of course, I can prove exactly the same thing with less than minus k instead of bigger than k. That's clear. But then this means that the collection of all pi in sim omega such that the sigma a pi n diverges by oscillation is a dense G delta set. Because this is just the intersection of all these sets. Look, I mean, if we intersect all these sets, then we have a countable intersection of open dense sets. So this is a dense G delta set. And also, it's completely clear that, I mean, if somebody is in the intersection of all this, if a pi is in the intersection of all this, then of course this must diverge by oscillation, by the way these sets here are defined, because we get bigger and smaller things. Okay. And why does this complete the proof? Well, look, if we have a non-meager set of permutations, then a non-meager set intersects every dense G delta, because the complement of a dense G delta is an F sigma meager set. So if you have a non-meager set, it must intersect every dense G delta. But for every such conditionally convergent series, this set is a dense G delta. So the non-meager set must intersect all of them. So actually what I'm saying here is that if I have a non-meager set of permutations, then this will be a witness for R. Okay. Next we come to B. B is the unbounding number. So let me just recall the definition. It's the smallest size of a family of functions in bare space, omega to the omega, such that for every function, there is a function in this family which is infinitely often above it. It's called the unbounding number because it's the smallest size of an unbounded family. So if we are less than b, it means we are bounded. So if a family of functions has size less than b, then we can find one function which is eventually above it. Now, b turns out to be a lower bound. Recall that with non-meager before we got an upper bound. So here we get a lower bound. If you look at this again from the point of view of computability, so it means that if x is high, if you have a high degree, then it's computably imperturbable. So highness implies this property here. because the highness, I mean, the classical notion of high corresponds to B here in this context. Okay, so let's prove this. Actually, the proof will be in 2 steps. Let's assume, so this proof is a little bit more difficult than the other ones, but I have enough time, so let's do that. I may have to skip some proof at some point, but that one I still can do. So let's assume we have an infinite subset of omega, and also we have a permutation. We make some definitions here. So let us say a permutation preserves a set if it, except for finitely many places, it preserves the order relation in this set. So it means that for almost all n and m in A, pi of n is less than pi of m. Of course, when I write like this for almost all n less than m in A, I mean that both n and m belong to A, and of course n is less than m, and for almost all means that, yeah, for almost all pairs of elements of A, this holds. That's what I mean. Okay, so basically it means that pi preserves the order of the elements of A. It doesn't mix them around. And we say that pi jumbles A if that's not the case. So if pi does not preserve A, so infinitely often it will sort of reverse the order of the elements of A. Now we define the jumbling number. That's just sort of additional or a definition which is not really needed, and I will say in a minute why it's not really needed, but which is helpful in this context. So the jumbling number is the smallest size of a family of permutations of omega, such that for every infinite subset of omega, there is somebody in this family which jumbles A. Now, what can we say about this number? Well, there are 2 claims. The first one is that this rearrangement number is above J, and the second one is actually that B is equal to J. So this J is not really needed. I said this because actually B and J are the same. So the 2 cardinals are the same. But it's still helpful because it's much easier, it's much more intuitive to show that J is below the rearrangement number. So, of course, these claims, 2 claims together, give me the theorem. That's obvious. And I will now sort of sketch the proofs of the claims. The first one is really simple. For the second one, I will actually only prove one inequality, the one which is needed to complete the theorem. So I will only prove B is less or equal than J. But it's reasonably standard. I mean, both directions are still reasonably standard arguments. Okay, so let's prove the first claim. J is less or equal than the rearrangement number. Here is still, again, the definition and also the theorem. Okay, so what do we do? Suppose we have a family of permutations which is of size strictly less than J. What we now have to do is to show that it's also of size strictly less than the rearrangement number. So what we have to do is we have to prove that this pi is not sufficient. Or we have to prove, to say it in other words, we have to prove that there's a conditionally convergent series such that all rearrangements by everybody from pi still converge to exactly the same limit. And that's what we will do now. Okay, so because the size of pi is less than J, it's strictly less than the jumbling numbers, just by looking at the definition here again, it does not have this property, so there exists an infinite subset of omega such that for every pi in pi, pi doesn't jumble A, so pi preserves A. So there exists this A in omega to the omega such that all pi in pi preserve A. That's just by the definition. And now let me list A in increasing enumeration as In. So the In are the increasing enumeration of A. And now, assume we are given an arbitrary conditionally convergent series AN. Of course, that one won't work, but I will now change it so that it will have the property I want. We define BK such that if K is equal to IN, then it will be AN. and it will be 0 otherwise. So what is this really doing? Maybe let's make a picture here. So here we have A0, A1, A2, etc. So again, we have 0, 1, 2, and at some point we have maybe this is equal to I0, I don't know. Maybe then we have I1, we have I2, and so on. So what I'm doing now is basically I put these values here, so they are sort of spread out, and everything in between is filled up by zeros. That's what we are doing. That's what this operation does. And now here, okay, so here we have the AN, and here we will have the BK. That's the sequence of BK. So it has lots of zeros, and then comes again a value of the A sequence. But of course, eventually every value of the A sequence will appear. So it's clear, that's the first fact here, that the sum of the BK will be the same as the sum of the AN, because I sum over the same things, except that I have put many zeros in between. So of course, again, this A BK in particular is conditionally convergent. However, and that's now the main point, for every pi in k, the sum over the BK is the same as the sum over the B pi k. And why is this true? This is because pi preserves A. So except for finitely many places, pi preserves the order of the IN. So it actually preserves, every pi preserves the order sort of these places here, and the rest are zeros. So what, of course, pi mixes things around here, but if you interchange zeros, it doesn't matter. But it will not interchange the order of these things, eventually, from some point onwards. But look, if you have a permutation, and the place where you have zeros, of course, don't matter, because they don't contribute. And the other stuff, we only have to sum about them. We only have to sum over the non-zero stuff, and except for finitely many places, the order of the non-zero stuff is not changed. But if in a series you only change finitely many places, and the tail remains the same, then it still converges to the same value. That's also easy to see. By finite changes, you cannot make a series converge to another value. So that's the point here. That's the end of the proof. And now I have to prove the other thing, which I mentioned. The claim 2 was B is equal to J. As I said already, let me only do 1/2 of this B less or equal than J. That's enough. This is, of course, not what I claim in claim 2, but this is enough to complete the proof of theorem 3, because then we have the inequalities B less or equal than J, J less or equal than double R. Okay. We proceed in a very similar way. So we start with a family of permutations of size less than B, and now we have to show that it also has size less than J. So it's not sufficient for the definition of the jumbling number. So we have to find some subset which is preserved by all permutations of pi. That's what we have to do. Let me define a function. If you have a permutation, we associate with this permutation a function f pi in the Bayer space. And there are two properties. First, I want that this function is strictly increasing, and also, well, that it f pi n always dominates n. And then I want that whenever, for every n, if m is less or equal than n, and on the other hand, k is bigger or equal than f pi n, then pi of m must be less than pi of k. Maybe you have to think 1 minute about this property, what it means, and actually also why it can be achieved. Suppose, you see, suppose we are at stage n. So we define this function recursively. We are at stage n, and now we want to define f pi of n. So we look at all the values pi of m, where m is less or equal than n. Of course, these are only finitely many, so they are somehow bounded. But also, because pi is a permutation, only finitely many values can be mapped by pi below this bound. So eventually, if we choose a k which is large enough, pi of k must be above this bound. And that's exactly what this is saying, that from some point onwards, for some chi b, so that's how we define f pi of n, such that for this k, from this k onwards, we are always above the earlier value. So this clearly can, I mean, such an f pi can be constructed. Okay, then because our family of permutations has size less than b, it's not an unbounded family. So there is a function in the Baire space which is eventually above all the f pi. That's just by definition of P and the fact that the size of pi is less than b. Then, using this G, we define a subset of the natural numbers, which is sort of a thin subset, so it's very spread out. And the condition is simply that an plus 1 must be bigger than G of an. So we start with a0, and then a1 is bigger than G of a0, and so on. And so we can create a subset of a sort of thin or spread out subset of the natural numbers. Now we show that all pi in pi preserve the set A, and then we are done, because then this means that pi is not a jumbling family. And so we wanted to show that the size of pi is also less than j. So that's not a jumbling family. Okay, but this is again simple because, okay, so what do we have to show that pi preserves A? What did that mean? This means that from some point onwards, pi does not change the order relationships of the elements of A. So this order relationship is only changed at finitely many places. So let's see. Let's assume that G of an is bigger or equal than f pi of an. Because G eventually dominates f pi, this is true for almost all n, except for a finite initial segment. Once you have this, it's easy to see, just using this definition here, then pi of an must be less than pi of an plus 1. And that's all that's needed. So from this point onwards, we always preserve the order relationship. Let's just see why this is true. You see, if G of an is bigger or equal than f pi of an, and then an plus 1 is bigger or equal than G of an, so in particular, an plus 1 is bigger or equal than f pi of an, but so this one will apply here. So this k, I mean, is of this form for f pi of an, and therefore, of course, pi of an is less than pi of an plus 1, just by this definition here. Okay, so this completes the proof or proof sketch of B is less or equal than R. Now let's see. Now we look again. So far I only looked at this cardinal. Now let me look at these two. They can be bigger. And I will say something about this in a minute. But also, so they also have a lower bound, but they have a better lower bound. And the lower bound they have is the dominating number. That's a cardinal which is bigger than the unbounding number. So what is the dominating number? The dominating number is the least size of a family of functions in the Baire space, such that for every such function, there's one in the family which dominates it, or which eventually dominates it. So from some point on, it's bigger. So for almost all n, oops, what happened? So for almost all n, Gn is less than Fn. Okay, so this is a lower bound for these two. And recall that for these two, we either required divergence to plus minus infinity or convergence to another finite number. And I'm not going to say, well, let me just say what it means. Because this is for both cardinals, it's actually also for the cardinal where we require either of the two properties, and that corresponds to weakly imperturbable. And so, and then also the cardinal D corresponds to the hyperimmune degrees. So it means that if X is hyperimmune, then it's weakly computably imperturbable. And this is, again, of course, a result in the other paper. And the proof is similar to the proof of Theorem 3. So I'm not going to give a sketch here. It's sort of similar arguments. Probably at this point, what I will do now is I will start to draw a diagram because we have many results, and somehow this, I think it starts getting confusing because we have too many results. So there is B, and this is below R, and this is below non-Miege. We will get one more result in a minute. Now B, so we go, kernels get bigger if we go up or we move to the right. So B is below D, and then of course this is below, now this is a little bit difficult to draw, but of course here we have as an upper bound Ri and Rf. And also here we have this as upper bound. I think that's sort of what we did so far. Of course, everything here is above Aleph 1. I should put Aleph 1 here, I guess, because I need a little bit more. And everything else is below the continuum. So I think here I can already complete the lines because I don't need any other cardinals. Okay, so this is what we got so far. If we look at these Highness notions, what we get corresponding here is high implies hyperimmune. So I tried to make a diagram which looks similar. This one looks is imperturbable. This is weakly imperturbable. And here is, I think that was weakly. So it was high or D and C. Okay, there's one more result. I think that's really the last result I will prove. Well, I'm not sure whether I should go into detail. So covering null is the least size of a family of nulls that's covering the real line. It's a definition. Covering null is also a lower bound. So that's what's still missing here. Let me put covering null here. And then the diagram goes like that. And of course, covering null corresponds to a Schnorr random. So here we have the Schnorr random. So a Schnorr random computes computably imperturbable. But notice, of course, and that's something which is not true in set theory, of course, high is stronger than Schnorr random. So we also have this implication. So actually, this theorem here is a strengthening of theorem 3 prime. But this is not true on the set theory side. So on the set theory side, these two are independent. So there are some places where this analogy breaks down. Okay, about the proof. Well, the proof is not very difficult, but it uses an old fact of Rademacher's lemma. If you have a sequence of reals, and now you look at the functions in 2 to the omega such that the sum over minus 1 to the fn Cn converges. So you have this sequence here, and you can think of as Cn as being all positive, and then you sort of attach minuses and pluses according to f. And then this set actually is always measurable, and it's either of measure 1 or 0, and it's exactly of measure 1 if the series of squares of the Cn converges, and otherwise it's of measure 0. That's an old fact. So in particular of the Cn, and that's how we will use it, if Cn is 1 over n, then we get here 1 over n squared, and of course that's absolutely convergent, so we are in this case. So if Cn is 1 over n, then this set here is measure 1. That's what I'm saying. Yes?
Is it also absolute convergent implies it's a squared convergence?
wait, if Cn is absolutely convergent,
Yes,
then the square is also of course converges.
okay,
Yeah, yeah. Because the square is eventually it's much smaller. So. Okay. So let's take any permutation, and now let us look at the series 1 over pi n squared. Of course, this, as I said, 1 over n squared is absolutely convergent, so every rearrangement also converges. Of course, this converges. We all know that. That's, again, something we learn in the first undergraduate year. Okay. Now, if we have such a pi, then we can look at the set A pi. So we look at the set of A of all f's such that -1 to the fn over pi n diverges. Now, this is a null set by Rademacher. Because in the convergent case, if this is convergent, then the places where this is converges of measure 1, so where it diverges is a null set. Okay, now, if we change this a little bit, here I put, instead of -1 to the fn, I put -1 to the f of pi n. This is also a null set. And this is simply because if you go for this, from this set to this set, this is a measure preserving bijection. And therefore, if this has measure null, that one also has measure null. Okay, now let's take a family of permutations of size less than covering null, and let's assume that the identity is in our family. So because our family has size less than covering null, and because all the B pi are null sets, the union over the B pi cannot be everything, because the definition of covering null was that it's a minimal size of a family of null sets which cover the real I. So this is smaller than covering null, so it cannot cover the real I. So what does it mean? It means we find a function in the Cantor space which does not belong to this union. And now we look for this particular function. We look at the series -1 to the fn over n. Now this must, of course, this is conditional. It's not absolutely convergent because it's like 1 over n, but it's, of course, conditionally convergent. Why is it conditionally convergent? Because f is not in this set and the identity belongs to pi, and therefore this one, it's not in this set, so this one does not diverge, so it converges. And actually by the same thing, because f is not in any of the B pi's, for every pi in pi, this one converges. So all the reorderings converge. Of course, they do not necessarily, we do not know whether they converge to the same value. This is not something which Rademacher's lemma says. So we only know that all of them converge. However, this is enough to see that RO is bigger or equal than covering null, because, of course, this means that none of them diverges by oscillation, and therefore recall that RO was the definition with divergence by oscillation, and therefore RO must be bigger than covering null. That's what we can infer from this argument. However, we established early in Theorem 1 that RO and R are the same cardinal, and therefore it follows that R is also bigger than covering null. So this is a little bit tricky. Once we are given Rademacher's lemma, it's actually quite short, but it's a little bit tricky argument. It uses something non-trivial. Okay. As a corollary, we get that D, it's consistent that D is less than R, for example. So what would I say here? Okay, so this is true in the random model. The random model makes covering null large, but it leaves everything here small. So we split this is what the random model does. It splits the diagram like that. So in particular, here we have consistency, and here we also have consistency. That's what I'm saying. Also, we get that it's consistent that covering null is less than R. This happens in the Lever-Heckler model. So for example, we can put it here, say Lever model. So we also get consistency here. Actually, this is not, I think something, this one also works in the decrease here. The other one, of course, doesn't work because high implies no random. And I think it's actually not known whether, the converse here should fail, but I think that's open as far as I know. So I have to look at the paper again. What we do not know, which is still an open question, and we are still sort of working on that, but in the new paper, in the new paper we do other things. We didn't solve this. So here we have a question, whether this is really, I do believe that it's consistent that this is smaller, and have some idea about the model, but it's actually not known. For Ri and Rf, we actually don't know any upper bounds. Of course, C, so that's the size of the continuum, is an obvious upper bound, but I don't know any other upper bound. Let me just recall the definition. Ri was where we require divergence to plus minus infinity. Okay, so what we do know is it's consistent that this is less than C. Actually, for both it's known. I mean, I will say this now. We can split the diagram here, but that's a little bit of work, and this is not like for the other consistency results, we just use the inequalities and then we appeal to some known models. Here we actually construct the model. So we start with a model of C bigger than omega 1, then we make a finite support iteration of a sigma-centered forcing of length omega 1. What does the forcing do? At each stage, you add a permutation pi such that for all ground model conditionally convergent series AN, the permuted series A pi n either diverges to plus infinity or to minus infinity. You just do it for all of them of the ground model. This actually needs some preliminary forcing. So to construct this forcing is not, there's a preliminary forcing, then you do this forcing sort of. But in any case, I mean, everything is sigma-centered here. And then the omega 1 permutations adjoined along the iteration will just be a witness of R equals omega 1. But we start with a model where the continuum is large. So the continuum, of course, will remain large because it's a CCC forcing. We don't collapse any cardinals. So that's fine. Let's see. So we can get the same thing for RF, but for RF it's actually even more work. So we can get RF less than C. We do something similar. This time I only know the forcing is sigma linked, which is a weaker property, but still much stronger than the countable chain condition. So again, cardinals are not collapsed. And for this one, I mean, we do something similar, but what we do is we use the Levi-Steinitz theorem, which is a finite dimensional version of Riemann's theorem. So there is some non-trivial theorem involved, actually. We use the Levi-Steinitz, or actually some lemmata which are used to prove Levi-Steinitz are sort of used to construct the forcing and to show that this forcing is actually sigma-linked. So this proof is actually quite interesting. And so that was also sort of the last result we proved for this paper. We still do not know what the relationship of these two is. But definitively, it's easier to make this one small than to make that one small. So I sort of conjecture this is below that one, but I don't really know. And I also conjecture that this is strictly less than that. I mean, if the sigma linkedness here is really necessary, if we can't do that one with sigma centered, if we can show that somehow, then this would actually establish this consistency here. Okay, I probably have something like 2 or 3 minutes, I guess. Right. Oh, so this is actually my last slide. So time-wise, I'm fine. I'm not going to prove any more theorems, and even the previous theorems were sort of proof sketches because the technical details there are much more complicated. Now, this is about another cardinal, actually, and this is the new paper, which we are right now writing. If you have a conditionally convergent series, then it has a divergent subseries. I mean, that's obvious because you can just, I mean, as I mentioned before, of course, the positive terms must converge to plus infinity, the negative terms must converge to minus infinity. So you could just use as x the positive terms, for example, or the negative terms only. So this always exists. So we can define again a cardinal. So you can ask how many subsets of omega do you actually need, such that for every conditionally convergent series, there is a subseries which is indexed by one set of this family such that it diverges. So it's a minimal size of a family of subsets of omega such that for every conditionally convergent series, there is somebody in the family such that if we look an x such that the sum over x of the AN diverges. There are also modifications of this where you want, there's a modification of this where you want divergence by oscillation, or one where you want divergence to plus minus infinity. Now, what do we get? I mean, this is quite similar. The curve is actually quite similar to that one, but it's actually not the same. So two things are still true. I'm not going to draw this in the diagram because I would mess it up. We proved before that covering null is below the rearrangement number, is below non-meager. The same thing is still true for the subseries number, basically the same. Well, here you have to work a little bit, because now it's not measure preserving anymore. But still, I mean, both inequalities are still true, and if you know the previous proof, basically you can also construct this proof. The third one was this one, and that's actually not true for the subseries number. I will mention this. But there is another lower bound for the subseries number, a lower bound which we do not have, or actually we don't know whether we have it for the rearrangement number, and that's the splitting number. So the splitting number is below the subseries number. The splitting number is the smallest family of subsets of omega, such that for every subset there is one in the family which splits it. Yeah, I'm out of time, sort of, so let me not say more about that. This is also a cardinal which, well, sits, I mean, it's independent. This cardinal is S is independent of B, and also independent of covering null, and it sits below the rest. Well, actually, we don't know its relationship to R. What we do know is that it's consistent that the subseries number is less than B, and this actually holds in the Lever model. And so this also means it's consistent that the subseries number is less than R. We do not know whether the converse is consistent. I would conjecture that maybe even this is true. Of course, it would be sufficient to establish that R is consistently strictly less than the splitting number. That would, of course, be much stronger than solving this problem here. Okay, I'm out of time and I'm done. Thanks. Sorry?
I have a philosophical question. So when I look at the development of that theory, then it was a big surprise that we have different cardinalities for the infinite.
Right, yes.
So we have the countable and the uncountable one.
Right.
And then Cantor tried to prove for many, many years in his life that there is nothing in between.
Right, yes.
That would became then the famous continuum hypothesis.
Right.
And then there was that kind of amazing proof that that is independent on
right.
that. So we can assume it is true. In what case, I guess all those numbers here are true inside?
Yes, in this case, everything is trivial. So everything collapses because this is Aleph1, which is at the bottom, and this is continuum at the top. Yeah, maybe I should have said this. Under CH, everything is trivial.
The continuous hypothesis is false, so there are
right.
numbers. And what I was always wondering, I mean, at some point, whenever I think about what kind of mathematics we are doing, then I like to map that to, I don't know, reality, to figure out which one is more appropriate, assuming it or not assuming it. So my philosophical question is, your results are giving any indication in what direction I should take?
What
no.
they say is, if you have here two cardinals, so whatever assumption you make on continuous difference event, this will always be below this. And this is the question here, which relations always hold. And if he says it is consistent, that for example this would be greater than this, that it means there is one model of set theory where this one is really larger than this. And more than this basic things, of course, one can make conditions. So is there a model of set theory where this is greater than this and this is equal to this, and such things you can also find?
I mean, on the philosophical side, this doesn't really, I mean, this doesn't answer the question, of course, and it also doesn't say anything about which one is more likely. And as Frank already said, so because we do not know, so one of the philosophies here is, of course, I mean, of what I've been talking about, and Frank already mentioned this, is that since we do not know, since we have these various possibilities, we really want to have theorems which are true anyway. So no matter which way it goes, it will be true. And most of the theorems I presented today actually were of this kind, because it just showed that this is less or equal than this, or this is, and this is, of course, this was all in ZFC. So most of this was in ZFC. But I mean, from these things, we don't get any insight about what should hold or what the continuum should be. I mean, I don't really see any reason why it should be Aleph 1, I mean. Because this is not, I mean, you see other things like the axiom of choice, you may still think by abstracting from what is true in the finite, this should also be true in the infinite. I mean, in the finite, the axiom of choice is true, so you may have some intuition about that, but the continuum hypothesis is even not true in the finite. I mean, if you look at the power set, you don't get the next Cardinal even in the finite. So why should it be true in the infinite? On the other hand, also, right, I mean, it's independent. And I don't think...
That's what I really liked about your talk. So it started from a very natural problem that has been solved by mathematicians maybe 500 years or longer. And now we get that there are some differences, whatever we assume. Yeah?
Right, yes.
Well, all the other constructs I have seen, they are really very abstract. Technically forms nothing, but this is...
Okay.
Yeah. Any other questions or comments? Then we thank the speaker again.